Hello again, my dear students. Now it's another lecture in our solid-state electronic course. Actually, this lecture is a turning point in our course. In the previous 3 chapters, we were dealing with what's called the semiconductor materials, where we have studied, maybe somehow in depth, some important theories related to the semiconductor materials, like the energy band diagram, the energy band gap, the band theory, the effective mass, the mass action law, the extrinsic and the intrinsic semiconductors, and all these stuff. And maybe we terminated these lectures with the drift diffusion model for current flow. Again, all these important theories are somehow related or associated to the materials. Now, starting from today and till the end of the semester, we will turn to the semiconductor devices. I mean, those electronic devices which is implemented using semiconductor materials. Herein, we are going to focus on in 4 different types with 4 different lectures. Starting from today's lecture, where we are considering the p-n junction or the electronic diode, then we are going to study the metal oxide semiconductor field effect transistor, or the MOSFET. After that, we are going to go to the bipolar junction transistor, or the BJT. And finally, we are going to study what's called the tunneling field effect transistor, or the TFET. Again, these are somehow one of the most famous devices, electronic devices, building units in our electronics industry using semiconductor material. So now please permit me to share my presentation and start our 4th chapter or 4th lecture with the title p-n junction. Okay, so great. I believe now you can see my PowerPoint presentation. Okay, this is perfect. So, sorry, I have to somehow to disable it. Make it again here. Okay, this one. And let me now turn my pointer and start our lecture. So this is chapter 4 with the semiconductor junctions or the p-n junctions. Let's flash back what we have learned related to the n-type and p-type semiconductor material. If you remember, we said that we have what's called an intrinsic semiconductor material where there is no impurities, no doping effect. The Fermi level is located typically in the middle of the semiconductor. Whenever we turn to be an extrinsic material, I mean, with the injection of impurities, these impurities can be a 5th group impurity or a 3rd group impurity. For the 5th group impurities, number of electrons increase, that's why we will call it an n-type. And now you will find that the Fermi level starts to go upward toward the conduction band. On the other case, or for the p-type case, what you will find that it's a reverse process when you add or when you inject the third group material, and then the Fermi level starts to go down to the valency band, as you can see. This is briefly what we have learned in the impact of the doping on the energy band. Now, let's imagine that you combine a p-type and n-type regions. So in the left-hand side, you have a p-type doped semiconductor material, and in the right-hand side, you have an n-type doped semiconductor material. And you are going now to merge, to allow you to mix these 2 materials together to form what's called a junction. Then the question will be how we could combine these 2 energy band diagrams. For example, if we do a plot like the one you can see now in the bottom of the page, you assume that there is a continuity in the energy band, in the conduction band, and the valency band. That the conduction band here is a conduction band there, but is this correct? Do you have any guarantee, or do you have any some sort of validations of the conduction band in the left-hand side or in the right-hand side in the N type is continuous with the conduction band in the P type, or in the p-hand side. So in order to do such a combination process, you have to have what's called a reference. I mean by a reference is a line, an energy level, which has the same definition in both the N region and the P region. This is very important. In order to have this reference, we have to have a common line. Let me return back, my dear students, 2 lectures ago. So I will, okay, so let me again share the screen. But I will disable my my presentation. Again, we still have our laser pointer, that's perfect. And then I will go to my previous lecture. For example, I will start to open lecture number, I think lecture number 2, for example. Let me check. Okay. So let's, yeah, here. So in this lecture, if you remember, my dear students will first introduce what's called the Fermi level. Here, if you remember. So let me turn it to be a full screen. We first introduce what's called the Fermi level. Here, as you can see from this definition, the definition of the Fermi level from a mathematical point of view is that it's a point where the probability to find an electron equals to 50%. If you remember, I told you now, this green curve represents the probability to find an electron. This red curve represents the probability to find a hole. Whenever these two curves met, whenever they overlap will overlap on the what's called the Fermi level. That's why whenever you have 2 choices and the 2 choices or the 2 probabilities are equal, then basically each one is 50%. So as a mathematical definition, if you remember, I told you that the definition or the mathematical definition of the Fermi level is simply the level at which the probability to find an electron is equal to 50%. Okay, that's great. Then we move to what's called the extrinsic and the intrinsic semiconductors. Basically the extrinsic, which is the N type, for example, here. Now let's again see this curve. Again, here we have the reddish curve for the probability to find an electron, and the blue curve is the probability to find a hole. And again, there is a point where both probability overlap, which is again the Fermi level. So the Fermi level is shifted, but it still has its mathematical definition as the level at which the probability to find an electron is equal to 50%. Then we go to the p-type case again. Now, as you can see, the probability to find an electron is the red curve. The probability to find a hole is a blue curve. Again, it's shifted downward toward the valency band, but it still has the same mathematical meaning that the probability to find an electron is 50%. So, very simple. What is common here is the Fermi level. Whenever you are going to combine any junction, PN junction, transistors, whatever device you are going to plot its energy band diagram, then you should have a fixed Fermi level. Those A+ students who have attended and listened to my previous lecture, when we start to solve a problem related to energy band diagram, I ask you a question related to what is the thermodynamic equilibrium. And we agree that the sign for a thermodynamic equilibrium is to have a flat Fermi level. So simply, this is what we are going to do now on our whiteboard. So now, let me stop sharing the screen for a while and let me go to this whiteboard. So I have a conduction level, a valency level. We have in the middle what's called the intrinsic Fermi level. And as this material is a p-type material, then your Fermi level will be shifted somehow here. So this is simply your p-type portion or your p-type part. Okay, perfect. Now let's draw the other part. Whenever I ask you in the exam to plot the energy band diagram of a p-n junction, you will repeat the same steps. You don't need to memorize anything. It's very easy and very simple. So this is the EC. This is the EF. And as we sorry, this is EV, not EF. I'm sorry, this is EV. Okay. And as we just mentioned, we have a Fermi level which is located in the middle. So we have here EF, I, and now this material is an n-type material. So you should expect a Fermi level more toward the conduction band, as you can see. So this is simply the case. Now we would like to measure, or not to measure, we would like to plot a unified energy band diagram for this p-n junction. The steps is very easy. Just start with plotting the Fermi level. So this is EF. And then start to plot everything with respect to this EF. So you will say that in this portion of the junction, it's a p-type material. So I should plot EV here and EC0. So as you can see here in this portion, EF, which is the red line, is closer to the EV with respect to the EC. On the other hand, you will make it like that. So, sorry, I have to make it slightly up. Okay, so this is EC, and this is EV, and here is, now this is a p-type material. What's happening in between? So you are going to link these two structures together to form the junction. Now you have the energy band diagram for a p-n junction. But we have a lot to say about this energy band diagram. What is now important for me, my dear students, is that to know how to plot such an important and interesting energy band. I believe that this is somehow easy. We start with the Fermi level, flat, then we start to plot EV and EC with respect to it, and then we make this linking between the ECs and the EVs. So we have a lot of questions here related to this important figure representing the energy band diagram. Again, my slides. So as a result, we have this energy band diagram. This is the P side, this is the N side, and there's something in between. Here you have to recall your first part of the module. That's why I told you in the beginning of my lectures that the first 2 or 3 lectures are fundamental lectures. We are going to use them across our module. So, what is the important points you have? Let's see. First, whenever you have a tilting, please remember these words from our previous lecture. Whenever you have a tilting, then there is an electrical field. And as far as there is an electrical field, that means there is a potential. Here you should stop me and say, where is the potential? It is just a p-n junction. I didn't insert any sort of potential. I didn't connect any sort of battery. It is just a p-n junction. That's why we will call this, my dear students, what's called a build in potential. So the word built-in potential means that you have an internal potential in the junction without having any external voltage source. Okay, then maybe your next question is, then I will have a current without having a source. Let's check. Okay, my dear students, from our previous lecture, we have learned that energy of electrons increase by going upward, while energy of holes increase by going downward. So here you have the p-type region, and here you have the n-type region. And here you have this tilting angle. So if there is an electron here, when in the place where I'm pointing my pointer, if there is an electron here, this electron will drift and move there, because this state includes lower potential with respect to this state. And if there is a hole here, again, in the place where I'm pointing my pointer, it will drift in this direction, because there is the energy here for the holes is lower than the energy in this state. So electrons will move from the left-hand side to the right-hand side, and holes will move from the right-hand side to the left-hand side. But do we have a lot of electrons in the left-hand side? Let's check. The left-hand side is a p-type region. So the total number of electrons is very few. It's a minority carrier. This is a very important point, my dear students. Whenever we have a p-type region, we have a huge number of electrons and a lower number of holes. So we call the big numbers, the lower number, which is holes, we call it the majority carrier. And we call those lower number of holes are the minority carrier. So in this region, we have more electrons, sorry, more holes and less electrons. While in the other region, we have majority of electrons and a minority of holes. So what you are going to do is to say that, okay, electrons will move from here to there, but it's very, very, very few amount of electrons, because here in the left-hand side, electrons are minority. Again, holes will left from the right-hand side to the left-hand side, but it's very, very, very few number of holes, because in the right-hand side, holes are minority. Okay. Finally, before proceeding to this, what about this region? If you remember, in our previous lecture, we have plotted what's called the static accumulation of a charge, which is somehow the second derivative of the energy. If you remember, my dear students, we say that by all means, it's very difficult for an electron to be occupied here, because if there is an electron here, it will automatically slide. It will automatically drift and go in the right-hand side. Similarly, if you have a hole there, it will automatically drift and go to the left-hand side. So this region turns to be a region where there is no electrons and holes. That's why we call this region a very important name, which is the depletion region. It turns to be, my dear students, please be very careful while listening to this portion. It turns to be an insulator. So please don't be depressed. It turns to be an insulator. It's true. Why? Because the definition of a conducting material is a conductance that is a material that have some huge amount of free electrons. When your free electrons is somehow medium, we call it a semiconductor. But when you have a region where there is no free electron, it's a region depleted from free carriers, so it turns to be an insulator. Okay, so what's happened typically is that holes are here on the left-hand side, and electrons are there on the right-hand side. So if I ask you now, if I have an electron here where I'm pointing my pointer, is this electron capable to go in here? The answer is simply no. It needs some energy. So this energy will push the electron to jump this depletion region and to go to the other side. Similarly, if you have a hole here, and I told you that, is this hole capable to move to the right-hand side? You all told me no. It needs an energy to jump this barrier. Again, this is another important terminology or another important term, which is a barrier. You have a barrier here. So to jump this barrier, you need energy to move. So basically, without any additional electrical energy or electrical force, or what's called under the thermodynamic equilibrium, majority electrons are not able to move from the left-hand side to the right-hand side, and majority of holes are not able to move from the right-hand side to the left-hand side. Again, my dear students, this is thermodynamic equilibrium. What is the sign that this energy band diagram is under thermodynamic equilibrium? Here, the Fermi level is flat, as you can see. Whenever you have a flat Fermi level, then your device is under thermodynamic equilibrium. And no current can move. Electrons are not able to move from the right-hand side to the left-hand side. Holes are not able to move from the left-hand side to the right-hand side due to this depletion region, due to this barrier. What I made here is very simple. This is a drift diffusion equation we just have concluded in the end of the previous lecture. And I told you that basically there is no current. So the Jn is equals to 0, Jp is equals to 0. Very makes sense. You just have a p-n junction, no applied electrical field, no applied external electrical field, so no current will move, and you have what's called a built-in potential or a built-in voltage. Maybe in the next slide we are going to investigate the value of this built-in voltage, but by now it's a built-in voltage, natural voltage due to this p-n junction. Okay, what is the next step? The next step actually is I would like to measure that, or not measure actually, I would like to plot the carrier concentration across the device. What do you mean by carrier concentration? Carrier concentration, my dear students, is simply N and P. The value of N and the value of P. So let's try to do it, and let's now stop sharing for a while. Okay. So this is your p-n junction, as you can see. I'll start to use my pen. So what I'm interested to plot now is that I'm interested to plot both the N, the electrons, and P, the holes. So whenever I'm going to make this plot, it's very easy. As you can see from this energy band diagram, we have three regions. This is the first region. This is the second region. And this is the third region. Here you have a flat energy band diagram. Then you have some sort of banding, tilting. Then you have another flat energy band. Let's first ignore this tilting region and start talking about the two flat regions, which are somehow, for us, more easy to deal with. Let's start with electrons first. So So electrons are majority here. This is an n-type region because EF is more closer to the EC. So you have a huge number of electrons. So for example, if I make some sort of doping using what ND, for example, doping, then the value of N here is simply ND. Okay, the other side of the material, this left extreme portion, is a p-type. So, for example, if the doping in the p-type is Na, then we will have a minority carrier, or N, equals to Ni squared over Na, which is, of course, small number with respect to P. Then, in between, we have something like that. Okay, what about holes? Here, this is a p-type. So the number of holes equals to Na. This is an n-type. So the number of holes equals to Ni squared over Na. And then we have this link. Now, in order to make it a common terminology, my dear students, we will make a very important note. Each time we will have a main character and a subscript. What do you mean? For example, this is a P region. So here, this is a P region. We don't need this anymore. This is a P region, and this is the N region. So when I would like to call the hole in the P region, I will call it P sub P. When I would like to call the holes, so the electrons in the P region, I will call it N sub P. When I would like to call the electrons in the N region, I will call it N sub N. When I would like to call the holes in the N region, I will call it P sub N. So the sub character here indicates the region. The main character indicates electrons or holes. And to state that this is under thermodynamic equilibrium, I will add node. So PP node means holes in the P region under thermodynamic equilibrium. PN nodes means holes in the N region under thermodynamic equilibrium, and so on. So this is a very important terminology. You have to know it very well because we are going to use it a lot. Okay, perfect. Let's turn back to our slides again. And I think we can move one step. Yes, this is the graph. This is typically the same graph we just plotted together, showing the electron and the hole concentration for an n-type and p-type region, as you can see. And this is the graph. Again, another interesting point. If I gave you this graph and I told you, please identify the region at which the material, or sorry, not the material, the junction is behaving like an intrinsic junction, intrinsic material. So this is the point. Can you see it? Why? At this point, n is equals to p. Whenever n is equals to p, then this is equals to ni. So you can add that this point is equals to ni because basically n is equals to p. So again, this is a very important point, my dear. So as you can see, this is some sort or some way to make some sort of analysis for the PM. Now I will terminate this part of my lecture. In the next part, we are going to investigate how we can calculate the value of this building potential, what is the impact of this potential, and how we are going to get rid from this potential and makes current flow. Because under thermodynamic equilibrium, current is equal to 0, as you can see. And now, in order to inject, in order to move current, we have to get rid from this barrier. Now, this is the end of part number 1 of this lecture. See you in the next lecture, inshallah. Thank you very much.